Hello and welcome back to the second video on variational inference. Well, part two. I am Chieh from Northeastern University. So in the last video, we talked about the basics of information theory, important for variational inference. Concepts such as information, that it's related to the probability of an event, or things such as entropy, which is the average of the information. And here's the equation accordingly, as well as if we are in the continuous domain, instead of a summation, we use the integration for differential entropy. Now, these concepts are very important, especially for variational inference, especially for this video, because it builds on top of it. Today, we're going to talk about a concept called KL divergence. The first time I mentioned KL divergence to my wife, she thought it was the vegetable kale divergence, which it actually stands for Kubeck-Leber divergence. Now, most of the time people call it as KL divergence, but I'm going to also tell you another name called relative entropy. Now, this is a much more descriptive name of what it's actually doing. So, what does it do? That's the real question. Well, it measures the distance between probability distributions, two probability distributions. So if you have two distributions, if they're very similar, the distance between them will be small because they're close to each other. If they're very different, the distance between them will be far away. Like for example here, if you look at P and Q, the KL divergence between them should be very, very small because they look very similar to each other. On the other hand, if you look at P and R, now obviously their KL divergence or their distance, it will be a lot larger. Now, when you want to write KL divergence, what you do is you write KL of P and Q. The way you kind of see it is like the KL divergence with respect to P against Q. Now, with respect to P. Now, this will become a very important concept later. But so whichever is the first one is the one that you're doing it with respect to. Okay, so like I said, KL divergence PQ should be small, but PR, PNR, PNR should be relatively large, right? Comparatively, I mean, if you were to try to compare them together. Now, remember that KL divergence is also called relative entropy. So when we're talking about distance and measuring how far away they are from each other, what we're using is actually entropy. How far are the entropy between them away from each other? Okay, so we're using entropy to measure the distance. So from that, you can kind of just picture how you could formulate this equation. And what makes the most amount of sense would be that, well, you just calculate the entropy of one, like this one, and subtract the entropy of the other one, which is actually makes a lot of sense. And it's very, very close to what we're doing. So over here, right, we find the entropy at HP, right here. And then over here, we find the entropy at HQ. So here's HQ, HP, and we say that KL divergence of for P with respect to P against Q is the entropy of Q subtract entropy of P. So like this, entropy of Q minus entropy of P. So I'll repeat that again. KL divergence with respect to P is HQ minus HP. Almost. That's not exactly the equation, but this is 99% of the equation already. Now, remember I told you that we are doing it with respect to P. Again, this is very important, with respect to, I repeat things because it's important, P. Now, that means we are looking at it in terms of P. Therefore, the probability we want to use when we're calculating the entropy is P. So we should be putting P here, and we should be putting P here. That's the only difference. And now this is the actual equation of KL divergence, and that's all you have to do. It's not that complicated. Like I said, relative to P, and notice how it's P here. Of course, if we had Q here, and now it's like Q here as the first one, then it's relative to Q. And the idea holds the same. Notice that the probability are with respect to Q. Of course, we also flip this and this because we're doing it with respect to Q instead. So if you know entropy, you essentially can know what KL divergence is of two probability distribution. You're basically finding the difference in entropy, and depending on which one you're taking with respect to, then you have to make sure you use the probability correctly. So the equation is actually really, really intuitive and self-explanatory. So, this formula is actually the KL divergence formula. However, this is kind of complicated. Most of the time you see a simplified version. What I mean is that they kind of like combine the terms and make it look nicer. So most of the time when you see KL divergence in Wikipedia or other sources, you will see it a different form, but exactly the same formula. So like this formula helps explain the idea of KL divergence, but now I'm going to simplify. I'm going to simplify this equation so that it's basically what you see normally. So over here, here's the equation that we derived right above the KL divergence. What happened is, notice that you can put the summation together and you can pull this term out. So I pulled them out. And then these two terms then organize here, right? Of course, if you remember from your calculus, the subtraction in logarithms is division. So you can, one of the properties is that you can put them together like this. And that's it. This is the form that you see. This sometimes is, this is the form you see, and sometimes they do it backwards. Like what they do is like they flip this. You see how over here Q is at the bottom, over here Q is at the top. So when you do that, because of the nature of logarithm, you have to put a negative here. But these two equations, they're actually identical. Just sometimes people write it this way, sometimes people write it this way. Rarely do people write it this way, but this way helps us understand how these two equations come about. Okay, so this is the equation for KL divergence. Oh yeah, notice the negative when I flip the two things over here. So now let's do like a really quick example, right? Over here is the same three distributions that we have been talking about. So if we want to find the KL divergence P and Q, then here's the equation that we just derived above. And we essentially take each one of them and sum them up. So there are 4 points here, 2, 3, 4, right? We want to sum them up. So the first one, the first point is 0.25 right here. And the numerator is 0.25. And then we look at over here, which is Q, see, QX1. So it's also 0.25. So the equation to look at is here, actually. Px1 times the log of px1 divided by qx1. So this is px1, this is qx1. And I just plug the number in. And then the second point, it's the same, you know, over here, 0.25, 0.25. And the third one is slightly different. This is still 0.25. But over here, which is qx3, is 0.26. And over here, the difference is 0.24. You might want to pause the video and study how I got this, but it's not really. I'm basically just following the formula here, which is the formula here. Okay, so if you were to, pull out a calculator to solve this whole thing, you will get a very small value. This one, 0.0004. And you should definitely make sure you can get this. I hope I didn't calculate this wrong, but I think this is it. But the idea, I use the same ideas, and I also calculate P and R. And notice that P and R is 0.295. And this is much, much larger. See, 0.295 is much larger than this, which says that the distance between these two is very far. And the distance between this is relatively close. That's the point. So, like I said, KL divergence measures, gives you like a measurement of how far things are, how far distributions are from each other. Okay, so now we have I want to go on to explaining some of the properties of KL divergence, namely two key ones here. The first one is that the KL divergence is always greater than 0. Now, if you think about it, if you want to know the distance between two things, it's always 0. If they're as close as possible, then 0 is the smallest possible value. Now, here's the equation, right? If this right here, we replace it with P, so that if P and Q are basically the same, well, they are the same. They're so close together, they're the same. Notice that this becomes 1, and log of 1 is always equal to 0. So 0 is the smallest possible distance. It doesn't get closer than that. Now, I can prove this mathematically, but it's really not that important how it's proven. And the second thing is that KL divergence is not symmetrical, the distance. What do I mean by that? Well, now the KL divergence from P to Q is not the same as Q to P. So what from P to Q is not the same from Q to P. So I remember the first time I heard this, like that, well, if you have a point A and point B, they're saying that the distance from here to here is not the same as distance from here to here. And needless to say, I was rather confused. But if you really think about it, that's true. That's kind of true in life. That if you're trying to drive somewhere from point here to here, well, due to traffic or due to the type of one-way roads, maybe like it is longer. So the key is actually to use relative distance instead to measure, like relative distance to measure the distance from point A to point B. And a very good example of this would be, like, if we look at it from this perspective, let's say we have point A and point B. Now, if we want to know the distance from point A to point B, let's look at it from point A's perspective, right? So from point A, everything in this neighborhood, everything it really sees is very, very close to it. So within its own neighborhood, it's only really this big. And now suddenly you go and ask point A, well, does point B look far to you? So they will look and they're like, oh, well, most of the time I see this. But suddenly they want us to they ask me about this. So from A's perspective, yeah, it's pretty far. But from point B going to point A, from that perspective, now, well, for B, everything is, you know, kind of far. So when you suddenly ask, well, point B, how far is point A from you? Well, it's not that much farther than, oh, it's other points. So no, it's not that far. Therefore, you can see that distance is actually relative, depending on the person whose perspective you're looking at. And from this, I can you can always prove this mathematically, but I think intuitively it's easy to understand that from point A to point B, it's not always the same from point B to point A, and therefore the KL divergence, the measurement of their distance, is not always the same. So so those two properties are the two properties of KL divergence are definitely important to keep in mind. Okay, now there is yeah, now I want to recap. So to recap, the KL divergence measures the distance between two probability distribution functions. Now, if KL divergence is equal to this equation, and it has two properties. Property number one is that the distance is always larger than 0. And property 2 says that the distance is not symmetrical. From A to B is not the same as B to A. So given that we've covered the KL divergence, there's one last thing that that will really help you in terms of using KL divergence to understand variational inference. So that is the relationship between log of x and the KL divergence. This is a very, very important relationship. And it's actually just manipulation of math, but you will see how I do it and the conclusion that we come up using this manipulation. So let's say we have a distribution, probability of z given x. And we don't know what this is. We don't know. We don't know. This is a big question mark. So we use q of z to estimate probability of z of x, given z given x. So, well, we don't know q as well, but let's say that we're using q to estimate this. Then if we're making an estimation, we can use KL divergence to measure the quality of the estimation, right? So if the estimation is really close to each other, then the KL divergence should be small. And if they're far away, then the KL divergence will say that it's big. So using KL divergence can help us quantify the quality of the estimation. And now we use the KL divergence, and here's the equation. Now, you might want to study this equation to make sure you come up with the same thing, but we're essentially just following the formula above. And to simplify, I don't want to write this every time, so I'm just going to write KL, and over here is the same. So let's start from this equation first. Okay. Now we know from conditional probability distribution, from condition probability, that the conditional is equal to the joint divided by the probability of x. And therefore, now notice this is here. I'm just going to plug this in. And if you plug this in, you get this form here, right here. You might want to slow down the video to do it step by step, but see that this is the same as here. And I just moved the rest of the portion here. And now I flip these two. I just switched the position. So QP instead of PQ. And after that, oh yeah, so over here I switched it, and because it's a logarithm, right? With multiplication, it's the same as summation. So I split that, and then I distribute. I multiply this here and multiply this here. Is that what I did? Oh no, that's not what I did. Sorry. First, so over here, right, is probability of x to the -1. So if we're talking about log, we can move this down, minus. And that's how I got minus log. So that's all I did from that step to this step. And now I finally distribute this. So you see, here is distributed. Of course, this is the summation across all z's. So if you sum up all z's in probability distribution, then it's equal to 1. So we can ignore this. This is not there anymore. Okay, and now we have the final form we care about. We can just move this over here to the other side of the equal sign. So minus turns into plus. And we have the form, the relationship between KL divergence and log P of x. And over here, this term here, we'll just sum it up and call it L for lower bound. Now, this relationship it's complicated. If you just look at it, you don't really know what it's doing. It's just a bunch of like mathematical like shifting. You shift this here, you shift this there. But what do we just do? Well, okay, well let's look at some characteristics of this. Well, you know that the P of x is the probability distribution. So it's always between 0 to 1. And the log of that is always a negative value. Always a negative value. Okay, that's what we know. This will always be a negative. And over here, right, this is the KL divergence. And one of its property is that it's always positive. It's always at least 0 or greater than 0. Okay. And this right here is called a lower bound. And that is, you can see it as the same equation as the negative KL divergence of these. Not really, but it's kind of like that. So since KL divergence is always positive, a negative over always positive is always negative. So you have 2 that's always negative and 1 that's always positive. That still doesn't tell us very much. Now let's draw this out. So over here, the KL divergence, there's some positive value. Let's call it 4. And that lower bound is some negative value. Let's call it 8. And this one, log of P of x, some negative value again. Let's say -4. Remember, it was probability of z given x. Z given x. So x is given. That this is what we're looking for. Now, if x is given, it means that, well, we know this already, so we can't change this. This is a fixed value. This is some fixed number. What could probably change around is q of z. By playing around with q of z, we can kind of manipulate these two values. Okay? Yeah, like I said, it's fixed and doesn't change. And L is the lower bound because it controls the KL divergence. Now, let me show you what I mean. Like, if this is fixed, by playing around with this, you essentially control this, controlling KL divergence. Right? Over here, like I said, this value is fixed. It's never going to change. However, if you start making the lower bound less negative, in other words, higher and larger value, right? -6 is larger than -8. So if you make L larger and larger, notice that the KL divergence start going lower and lower, right? So L controls the KL divergence with the inverse proportion. L goes up, KL goes down, like that. So like I said here, by making the lower bound L less negative, or in other words, larger, we are simultaneously reducing the KL divergence. And when we reduce the KL divergence, the estimation between Q and P of ZX becomes better. Now remember, the KL divergence was the KL divergence. Where was it? KL divergence. Yeah, here it is. It was the KL divergence between this and this. P of Z given X and Q of Z. So we're using Q to estimate P. So the smaller the KL divergence, the closer the estimation. Okay? Smaller the KL divergence, the closer the estimation. Let me see. Smaller, larger. Okay, so we want this to be as small as possible, but if we make this L as large as possible, that's the same as making KL as small as possible. That is the probably one of the most fundamental point. That here's the key point. That is the key point. When we're approximating a conditional probability using Q of Z, instead of minimizing the KL divergence, it's the same as maximizing this. So minimizing KL is the same as maximizing L. And it's much easier, much easier to deal with lower bound than KL divergence. Like KL divergence is hard. Lower bound, it's easier. Now, why is that? Well, most of the time, we have a joint probability distribution. But what we don't have is the conditional. This is what we're estimating. Like we literally don't know this. So, but this one, most of the time we do have. And therefore, it's a lot easier to deal with this maximization or minimization when you actually have the variable. So that is the key point. And if you want to understand variational inference, you must understand this point, that maximizing this is the same as minimizing this from the math that we have done. And that's the point. In the next video, we'll move on into more deeper into variational inference. So all right, thank you.